Hi, it's time for another math easy solution. Today we're going to discuss part B, or the second part of the example 2 video on seasonal growth, which is another model for population growth, and look at basically solve part B. But first I'll quickly recap my last video, example 2 part A. And I'll do that by just reading out the example again. So basically the example states, suppose we alter the differential equation from my last video, example 1, and this one was, in example 1, was basically the same equation here, except here we square this trigonometric function. So as follows. So if we have a differential equation like this, dp over dt equals to k times p, where k is just a proportionality constant, p is population, t is time. Then the cosine squared. In example 1, there's no square. We have cosine squared of r, another constant, times t minus phi, another constant. And given the initial value p of t is equal to 0 is just p naught. So part A was asking to solve this differential equation with the help of a table of integrals or a computer algebra system. I just solved that manually, and you could check that in my earlier video, my last video. I'll put the link below. And then, and basically I wrote down that solution here. This is the solution from my last video. And now part B states, graph the solution for several values of k, r, and phi. How do the values of k, r, and phi, again, phi is just a Greek symbol, Greek alphabet symbol called phi, affect the solution? And then it says, what can you say about the limit as t approaches infinity of p of t in this case? So let's just plot these out. So first thing, we have to graph the solution for various values of this. And what I did was I made an Excel sheet like this, and I'll put a link to this in the description below, where you can go ahead and let's move this over there, where you can go ahead and download and view it as well. So here is the graph like this. This is for different values. So for case 1, we have this one. I set all of the initial populations just to 1 to make it easier to graph. And then for this case, I made the k constants, the k constant all 0.5, and then r all 2, and then I varied here. This one is varying the phi. But let's just go with what I'll do here is I'll copy this, I'll paste this one here, and then as you see, everything changes. And I'll change k first, and then 1.5. And as you see, everything changes here. This p of 1, here's the giant equation. You put that all in there. This is just the population model here. This is simplify f of t is equal to this, etc. for time all the way from 0 to 11. So anyways, graphing this, and then in this case I vary k, make everything else constant, and then you'll see what happens. So I did this, and then let me just delete. Let me just move everything up. So first, what I did, let's consider varying k while keeping the other terms constant. So this is what, this is the results of my analysis and or just graphing the solutions. So varying k, what we end up getting is, if we vary this and make everything constant, this one is just pi over 2. That's what phi is. So we get this one is p of 1. That's just k equals to 0.5. That's the only thing, and then we change the k is to 1. So as you can see, it shifts this to the left, and then this one makes it more steep. So this is k equals to 1.5. And from this we know that, well, as an increase in k stretches the graph of p vertically while maintaining p of 0 equals p naught. So this is the value there, p0 equals 1. So p0 just stays like that. And then as you can see, it just makes it, when you change k, it just makes it more and more steep. And in the second part, I varied r while keeping the other terms constant here. So if you do that and make this 0.5, 1, and 2, we can even go here and so just make this as 1. Actually, no, not 1. Let's make this at 0.5. So what I did was make this 0.5, and as you can see, the graph change. And then this one, I made this 1, And actually, let's see what I made. So I made this 0.5, 1, and 2. So going back here, 0.5, 1, and 2. So as you see, everything changes like that. Copy that, paste it into this document. And so this one is constant and changes the others. And as you can see here, what we have, this one is at R is equal to 0.5. So as you can see here, this one is more broad, and there's less curves in it, like that. R is 0.5, and then when we increase R, so the second one here, this is R equals to 1. As you can see, there is a compression here of basically this is the period or the compression horizontally. So this one has more curves to it, and then when R is equal to 2, which is P of 3, that's this dashed line, R equals to 2, it's even more compressed. And basically as stated here, an increase in R compresses the graph horizontally, similar to changing the period in example 1. And now I'll go over example 1 right here. Just to recap, example 1, this was an increase in R, the amplitude and period changes. Period is just the horizontal distance of a single wave. So when you go from R to 2, 3, we're just making more waves. So here this one is less. So similar to example 1. So I'll just go back here. And now let's vary phi while keeping the other terms constant. And phi here, so I made these all like this, and then I varied these ones. So this is pi over 12, just a big, or just divided by 12, just to see that when you change when you change the angle of phi, nothing really changes much. This is pi over 2. This is just pi. And here we can go and type that in. I think this was 2. So this is pi over 12. This is pi over 2, and this one is yeah, that's pi. So we get something that looks like this, and then if I copy and paste this here, so there is our pi over 12. So let's see if this is the right one. Yeah, 0.262. Everything is the same, so pi over 12, and then the second one, this is pi over 2, dashed line is pi. So as you can see, when you increase it, it just basically, everything just gets shifted a tiny bit, and as an example 1, a change in phi only makes slight adjustments in the growth of p. It's changing, but not too much. Yeah, for example, when we increase, so we got pi over 12 the smallest here, we increase it to pi over 2, then it's yeah, it just decreases a tiny bit here, but it goes up and down, so it's not really changing much, and it still starts off here, so it's not changing too much. As an example 1, if I go back to example 1, when we change these get just shifted around. These are still the same starting point. Everything just gets shifted slightly. This one's actually shifted more so than this one, but in this squared one, it doesn't change as much as an example 1. Yeah, so now let's look at finding the limit as t approaches infinity of the population. So that's asking here, what can you say about the limit as t approaches infinity of p of t in this case? And recall from example 1 that when we didn't have the square, the limit did not exist because it would just fluctuate up and down, and you don't actually get an infinite number. It just does not exist. So what we have now is, let's just look at this limit as t approaches infinity of p of t. This is the same thing as writing limit as t approaches infinity of p0 e of f of t. And now the only thing that's a function of t is inside there, so this is the same thing as writing limit, actually no, we could just write the limit inside. So the same thing as writing p0 e to the limit as t approaches infinity of f of t. Yeah, so now we'll just have to look at this case first, just the top part there. So limit as t approaches infinity of f of t. Yeah, now this equals to the limit as t approaches infinity. Now we could just plug in our value for f of t from example 1 from example 2 part A. we have k over 2t, then k over 4r sine 2 rt minus phi plus sine 2 phi. So it's just a giant number like that. So let's just write that down. If I remember, k over 2t, and I'll put this giant bracket, plus, so we have plus here, k over 4r, and then we have a bracket sine of 2 rt minus phi plus sine of 2 phi, like this, like that. And now let's just quickly check if I wrote this right. Just is pretty tedious. Okay, so it looks about right. Okay, so anyways, so now when we simplify this even further, we just have to put this limit inside wherever there's actually a t variable. Yes, so if I just put this here, this is going to be broken down into limit as t approaches infinity, and put that into this t variable area, k over 2 times t, and then plus, and now what I'll do is I'll expand this and I'll put this limit inside this sine. That's only part where there's a t here. This one doesn't have one. So this equals 2, I'll just take the constant out, for k over 4r, and then we have this limit as t approaches infinity of this sine 2, and I'll just put this big bracket like that, sine 2 rt minus phi, and then expand this here. So since we expanded it, we'll have the k over 4r sine 2 phi, like this. So what we have is 3 terms here. This one doesn't have a limit there because there's no t, so the limit is just going to be itself there. So the first term we have as t approaches infinity, k over 2 is just a constant, so then t is approaching infinity. So this first term we have approaching infinity, and now what we have to do is look at this second term. Well, first one, this one is just a finite number. It's just a constant. Yeah, this is just going to be a constant number or a finite number. And now we just have to look at this part here. This is just a constant, it's not going to change anything. And then there's a sine 2 times rt minus phi. So let's look at this part here. So if we recall the sine function, so recall let's draw this out. So if we have f, y, and x, the sine function looks something like this, and it keeps going. Let's draw this a bit better. Keeps going, etc. And then this is our sine of x function, and then the maximum height is at plus 1, like that, and touches all the way here. Draw this neater. And then the lowest part of it as well over here, etc. Here is not the scale, but anyway, this is a negative 1. So basically, when you keep going, all it's doing is alternating from 1 to negative 1. So what we could write here is that this is oscillates from, or this part in here, the limit oscillates from negative 1 to positive 1. So what this means is this is, well, just a finite number still. So I'll write as yeah, so even though it's not finite, because as you're approaching infinity, it's just going up from negative 1 to 1, but it's not going to affect infinity here. So as you're approaching this, the whole thing's approaching infinity, you're going to either plus or minus 1 or a number in between, plus another finite number, so that this infinity just overtakes everything, and you're just approaching infinity. So what negative 1, infinity minus negative 1 is not going to change anything, and infinity plus 1 won't change anything either. So what this means is, thus the limit as t approaches infinity of f of t equals to infinity. So this approaches infinity, and then what we have is, now when we look at the limit as t approaches infinity for p of t, this equals to the limit as t approaches infinity of p naught or p0 e to the power of f of t. So what we have is a case where you have e is approaching, you have e to the infinity, as t approaches infinity, f of t is approaching infinity. Write this better. So then this e to the power of infinity is just approaching infinity. So we have this whole thing is just equal to infinity. So we get limit as t approaches infinity of p of t is equal to infinity, like that. Yeah, so in the long run, you're just still approaching infinity, and then as you can see from the graphs, it's gonna be approaching it like this up and down. Well, it doesn't actually ever decrease, it just goes flat line, goes up, flat line, etc. It just goes like this, but keeps going to infinity population. So yeah, that's all for today. Hopefully you enjoyed and followed through. It's pretty extensive, a pretty interesting analysis on these seasonal growth models, and that by just adding this square to the cosine or trigonomic function in the model, it goes to infinity. Before it would have no limit, just goes up and down, and see how it changes so much the solutions. It just keeps increasing, because again the square, you always have a positive value for the trig function. Anyways, that's all for today. If you learn, like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another math easy solution.